So now let's think about a pendulum, because it's going to behave similar too. Because we have a mass on here at some angle theta, and so mg pulls down. We got tension like that. We know it's going to swing down here, but it's the entire time it's to the left, it's accelerating downwards. So that means when it reaches the bottom, it's moving. So it's going to overshoot, come up over here, and it's going to be the same height it was originally. We know that from assuming it doesn't lose any energy through air resistance or anything. And then it's going to swing back down and go back and forth and back and forth and back and forth. And so that's going to look very similar. That's going to be oscillatory motion also. So let's see if we can describe that. Let's see if we can find the period of a pendulum. Okay. And so free body diagram, we look at it and we say, okay, we got mg pulling down, we got tension. Now the motion is in this direction right there. So if this is at some angle theta, then the component of the weight in the direction of motion is mg sine theta. So that's going to equal ma. So the A is going to be equal to g sine theta. Well, really, it should be negative g sine theta, because if that direction is negative, the motion is positive. So it's in the opposite direction. So really, this should be minus g sine theta. Okay. Now, the problem is A, okay, if this is going to be r times alpha, because this is going to be an angular thing. And so r, what is r? R is going to be the length of the pendulum. So we can rewrite that as L alpha equals minus g sine theta. So alpha equals minus g over L sine theta. Okay, now that's a very difficult differential equation to solve, because we've got on the left-hand side the second derivative of theta respect to time equals minus g over L sine theta. Okay, so that's going to be difficult to solve, because on one side you have a linear thing, on the other side a trig function. And so how do we do that? Well, this is where Calculus 2 comes in, because in Calculus 2 you talk about series expansions, Taylor series and so forth. And so one of the things you discover is that sine theta can be written as a sum of an infinite number of terms, a series. So it's equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7 over 7 factorial plus theta to the 9 over 9 factorial minus theta to the 11 over 11 factorial, etc. It goes on forever. The only thing is, it's always the odd terms here. And now, theta, this expansion only works if theta is in radians. Well, let's think about it. So, suppose we don't have a very big angle. So suppose we keep the angle fairly small. So if theta is about 0.1 radians, theta cubed be 0.001. And then we divide by 3 factorial, that's 6. So that means this is less than 0.0002. Fourth decimal spot. We rarely go out to the 4th decimal spot. Theta to the 5th would be 10 to the minus 5 divided by 5 factorial, that's 120. So that's going to be smaller than 10 to the minus 7. We never go out to the 7th decimal spot. Theta to the 7th is going to be 10 to the minus 7. Then you divide by 7 factorial, it's even smaller. So if we only keep to 3 decimals, then all these terms are changing way out there. So we can make an approximation that sine theta is approximately theta if theta is small. So we call this the small angle approximation. Okay, so as long as our pendulum is kept to a fairly reasonable small angle, then we can now approximate and say that this equation that we just had, and that's a second derivative of theta, the alpha, the second derivative of theta with respect to time squared equals minus G over L sine theta. We can approximate that as, so for small angles, minus G over L theta. Okay, so for small angles, well, small angle doesn't have to be all that small. I mean, small angle could be 10 degrees, 20 degrees, 30 degrees. As long as we're fairly small, then this is going to be a good approximation. And so now that differential equation we recognize. Now that differential equation is going to be theta is some amplitude times the cosine omega t. And then omega is going to be the square root G over L. So that means the period is going to be 2 pi square root L over G. And so the period of a pendulum depends only on the length of the pendulum and on G. And so that pendulum right there is dependent only on the length and on G. And so that's it does not depend on the mass. If you double the mass of what's swinging, it has no effect because there's no m in the equation right there. Now, this is an interesting thing because when the astronauts went to the moon, they shoved a flag into the lunar regolith. Now, obviously, it's going to just hang there limply because there's no air. And so what they did was they had a little bar that stuck off to the side, and the flag was hanging from the bar. Well, what happened was, as they were shoving it into the ground there, that they had to wiggle this thing to go in, and so this thing started oscillating. And so some of the naysayers, they say, well, we didn't go to the moon. Look at this. They see the flag's waving. Okay, well, it turns out the interesting thing is that it's not waving very fast because the period of that swing, because that's acting like a pendulum, is going to be equal to 2 pi square root L over G. G is very small on the moon, so that means a very large period. And people say, oh, but that's because they slowed down the film. Yeah, but you can see the astronauts moving over here, and you can see them accelerate as they step and they jump, and it turns out the spacesuits are very hard to actually walk in, so that what they did was they like hopped like little rabbits, and so you can actually measure G from there, from that motion right there. But this is not G, this is square root of G that's in this equation, so it's not linear. So it's not what you would expect if you slowed down the film. So all the people that insisted that the flag waving back and forth proved that it was not on the moon. Actually, if you look at the videos and you measure the G from the motion of the astronauts and you use that in the equation up here, it turns out to be ironclad proof that this was done on the moon.